Hey team, I think we're live. Great to have you once again. For those in Australia, good morning. For those in probably most of the rest of the world, maybe New Zealand accepted, good evening or good afternoon, whatever it happens to be. Hope you're all having a good weekend so far. All right, let's make a bit of a start. So, what I'm going to be talking about today is decoders. Or triggers, or trigger patterns, or they go by a lot of different names, but they all generally mean the same thing. As always with this session, by the way, do feel free, in fact more than free, I would encourage you to drop any questions in chat if you've got anything in particular you want to ask about. What a crank or a trigger pattern is something that gives the ECU basically two pieces of information, and that they're really the two main goals of any trigger pattern, regardless of what it happens to be. One is RPM, and that's true for every single crank pattern I've ever seen. All of them are about giving the speed of the engine, which we obviously need to know for an ECU. And the other that virtually all trigger patterns give, although there is one or two exceptions to that, is the crank angle. Now I say there are some exceptions to that because very, very basic systems that are using, say, just a distributor and just giving a certain number of pulses per revolution of that distributor will provide RPM information, but won't provide any crank angle information. There's no way for the ECU to actually know where the engine is. Getting into more detail about that, there's patterns that operate within 360 degrees, and there's patterns that operate within 720 degrees. So 720 degrees being, assuming for a 4-stroke engine here, one full cycle. So sometimes we know the crank angle within 360 degrees only, and that's generally if we just have a trigger on the crank itself. And other times we can know the crank pattern within, or the crank angle within 720 degrees. And then to do that, we virtually always need to have a cam trigger as well. So sometimes we can have one input just for the crank. Sometimes we can have two. Sometimes we can actually have two inputs, but still not necessarily be able to determine the actual crank angle. So we still are limited to 720 degrees. To 360 degrees. But those cases are a little bit more rare. Okay, so what I'm going to do today is walk through some of the basics of a trigger pattern that I've just written, which is the DSM 420A pattern. I've chosen that one because it's actually it's a neat little pattern that's not too complex, and it's also fresh in my mind because I just wrote it probably about 2 weeks ago. I think I did that one. So that's what I'm going to be walking through today. I'm going to talk about what that pattern is and how we gather the information about that pattern, and I'm going to show you what the code looks like. I'm also going to be showing a little bit on stim patterns, so with argstim and those sorts of things. I'm not going to go into a whole heap of detail on argstim. I debated about whether that was something I should really spend a lot of time on or not, but it's a topic that you could talk for an hour on. I've got some fairly grand plans for changes that I want to make to argstim, which will hopefully make things a little bit easier for anyone wanting to develop their own patterns, and a little bit easier to use. But I don't have those in place yet, obviously. I've just got to find some time to do that. But I will talk a little bit about argstim and how it works, and more though, what it does and why it's useful. All right, so what are we talking about? This is a typical example of a very, very common style of crank trigger. It's called a missing tooth wheel here for obvious reasons. This particular one is a 60 minus 2 wheel. So if you can imagine that these two teeth down here were not missing, and you counted all the teeth going around, you'd have 60. In this case, we call it a 60 minus 2 because the two here are missing. And this is what we use to determine when a full revolution has completed and what the angle of the engine actually is. Very interesting question in the chat here. Interested in your view on resolution of the encoders. What is the best bang for buck in regards to processing overhead versus timing and accuracy? That is a really good question. And I do have a very strong opinion on that. So this question is around how many teeth do we have here, that the more teeth we have, the better resolution and the better accuracy that we can determine the crank angle at any given time, and the speed for that matter. There is a point though of diminishing returns, and the more teeth you have, the more processing overhead it takes. There are patterns that have up to 360 windows in them per cam revolution, so that's 360 windows every 720 degrees. That's the classic old Nissan 360 pattern. There's also ones that work down to sort of 4 teeth, which is a good example of that would be the Miata pattern, which is very, very low resolution. Sounds really muffled. Hold on, let me have a look at my audio. Is the audio coming through fine for everyone else? Or we also seem to have a couple that have audio problems. I'm not sure what it is. I'll keep going, but Chris, if you're still having troubles hearing me, just let me know. To give another example of trigger pattern, this is a 36 minus 2 minus 2 minus 2, which is really a bit of a mouthful to say, and it's an interesting sort of pattern, but we see that it's got multiple sets of missing teeth, including some that are concurrent to one another. You do sacrifice some resolution in those areas, obviously, because you don't have teeth there, but patterns like this have the advantage that if we look back at the 60 minus 2 wheel, for every crank revolution, assuming that this has been located on the crank, we can only get sync on the engine after we see this gap here. So it has to take, or has to complete a full revolution, at minimum a full revolution, of the engine before we're able to actually see or be able to gain sync in the ECU. Triggers like this one give the have the advantage that we need at most half a revolution before we can see what's going on. We can determine whether we're at a single one because the next tooth after it will come immediately, or if the next tooth after it has another big gap, we know that we're over here in this part of the cycle. So those are just a couple of really basic and common trigger patterns that we see. I just wanted to really give them as examples of what's out there, and some of the more common ones that we do see. What I'm going to be talking about today though is the DSM trigger wheel, which looks like this here. Unfortunately, I could not find a single photo of this trigger, as in an actual real one rather than an illustration. My understanding is that these sit on the inner part of the crank, but like I said, I've never actually seen one physically, and that is a perfect example of why these trigger patterns sometimes can be a little bit difficult to work with. You're often trying to code up something around a trigger that you've never seen, that you've never used on a vehicle that you possibly isn't even in your country. We don't have a lot of these engines around, although we do have some Neons still in service, amazingly. But you can see that this pattern here is very different to what we saw with either the 60 minus 2 or the 36 minus 2 minus 2. Okay, volume is a little bit low. Okay, let me get a little bit close to the mic and turn the volume of my mic up just a bit. All right. Now, some of the ways it differs here is that we don't have a consistent tooth pattern all the way around the trigger. What we've got are a section here and a section here and a couple of big other notches. And this was an interesting one. When I started looking at it, I wondered why this was the case, and I wasn't quite sure why why they would have gaps like this and wouldn't just include the trigger all the way around. It's sort of come to light as I've worked through what the pattern looks like, and why this exists, and it does make some sort of weird sense. And it's a pattern I find is actually quite nice, and it works reasonably well for what it is, which is quite low resolution, but it has a couple of tricks up its sleeve that makes it work. So when we want to start looking at a trigger pattern, we need to find something like that. That's the most basic information that we need to be able to start working. Ideally though, we're also going to have something that looks like this. And this is a scope tracing of what that pattern looks like when it's spinning, and it also contains, most crucially here, the angles that all those teeth represent. Now I'm just going to make one comment that I meant to make at the start actually and forgot, that I put trigger patterns into one of two categories. There's generic patterns and there's application specific patterns. If we look at the 60-2 wheel again, this is a generic pattern, and it's an instance where some OEMs have used this, and it's a common one. You know, BMW's had these for a while, and no doubt there were others. But it's also a very, very common fitment in the aftermarket world, and this is a perfect example. It's an aftermarket trigger wheel here. It's generic because it won't be the same on every engine. Where this gap is in relation to, say, cylinder 1 top dead center will vary on different engines, and that has to be taken into account in a couple of different ways when we write the trigger pattern. On the other hand, when we look at the 420A pattern here, this will always be the crank angles for a given location, or for a given pulse train. It will never vary, it will never move. That there can be some wiggle room in terms of the CAS adjustment and those sorts of things that will, there might be a little bit of adjustment on the trigger wheel itself, but this is what it should be set up as. And we can make an assumption that when we see this particular pulse train, that's what we're going to have in terms of angles, and we can be definite about it. So that's a real advantage, and it's much simpler to write a decoder pattern that's specific like this, that you know is never going to change. As soon as you have a generic pattern, there's a lot of different scenarios that you have to start taking into account that aren't necessarily obvious at first glance. Okay, just to touch on that question before about resolution, I will come back to that in a minute. It'll make more sense in a little bit when I start talking about the code. So the first step that we have when we're wanting to develop a new trigger pattern, regardless of what that trigger pattern happens to be, is being able to reproduce that in a way that we can test on the bench. So in this case, that's going to be the creation of a stim pattern. I tend to use a piece of software called ArduStim, which is terrific. It has its flaws. It's a little bit unmaintained at the moment, so it can be a little bit tricky to work with, but it does allow you to fairly easily create new patterns, and I'll show you what those patterns look like in just a second, that we can then use as an input to our Arduino on the bench, that we can then test and write the pattern against. And that's crucial. Without that, you can't write a trigger pattern. It really is that simple. So what does creating one of these patterns look like? Let me jump into here. I hate bringing up Excel because there is absolutely nothing worse than an Excel spreadsheet. But I've found the easiest way to do it. I set up these pages to spit out this data here, which is a series of zeros, ones, twos, and threes. How do I zoom in here? Let's see. Helps if I can type. It's a Sunday morning. I was up too late last night watching the F1. That's my excuse anyway. Okay, so what these numbers represent is a 0 means no tooth whatsoever. So that would be a low period or a low edge on the tooth. So it would be this area here or this area under here. A 1, we have a 1 here, represents that the crank trigger is high. So this one down here, so this is the crank signal on the bottom and the cam signal at the top. A 1 in RGStim represents that the crank signal should go high. And so we see this pattern here of 1, 0, 1, 0. Now I've given this stim pattern a resolution of 5 degrees. You can see that each row here represents a change of 5 crank degrees. So if I want a tooth to stay high for 10 degrees, I need to keep it a 1 here for 2 rows. If I go back to 0, we get 10 degrees of no crank trigger. The 2s in this, as you might have guessed, represent the cam signal. So if we've got a 2, then we've got the cam signal going high as well. If we have a 3 over here, it means that both the cam signal and the crank signal should be high. So what I do is simply have a crank column, a cam column, and a totals column. I put a 1 in this column if the crank should be high. I put a 2 in this column if the cam should be high, and you get a total at the other end, which is either a 0, a 1, a 2, or a 3. All I then do is concatenate all of these together over here, and there are, if we go down, angles all the way down to 716 in this case. And the sharp-eyed observers amongst you might have noticed that I didn't start at 0 up here. I started at 1. Normally I would start one of these at 0 when I create these patterns, but there's a very good reason for this pattern that I didn't, and I'll show you what that is. If we jump back to the analysis diagram here, and normally, by the way, this kind of diagram can be found hopefully in the workshop manual. Most workshop manuals will have something like this to aid in diagnosis. If not, you can generally find them around the net, depending on how common the particular pattern that you're looking at is. We see in this case that if we're going to look at the falling edge, and we should, because that's what all these angles represent, we can see that the tooth just before top dead center here, its falling edge takes place at 9 degrees before top dead center. So 9 degrees before top dead center would be, if you can do your maths, 711 degrees absolute, or after top dead center. Because we're using, or because I'm using 5 degrees per row, go down the bottom here again, we can see that I've got one row that matches that tooth, and we can see that it's a 1 at 711 degrees, but at 716 degrees it's gone back to 0, and that's what represents that that drop that we saw for that particular tooth. Now adding another 5 degrees onto that would obviously be 721, which puts us right back to the start of 1 degree. So that's how I personally like to put together these RGStim patterns. You can write them in different ways and come up with different methods of putting them together, but ultimately the outcome needs to be this, a table of numbers that represent a certain number of degrees, in this case 5 degrees for every number that's shown here. You can do it in Excel, you can do it presumably any other number of ways. Should it have gone to 0 at 711? Interesting question. No, it shouldn't have. These are still crank degrees. Sorry, shouldn't it have gone to 0 at 711? You can do it either way. I get where you're going here. All it's going to do is offset the pattern 5 degrees. In my head, it's clearer to say that pattern went to all the way up to 711, and anything past 711 is where it drops. So it really won't matter. All it's going to do is move that pattern 5 degrees, and we just that makes no difference to the ECU. It's just happening at a slightly different time, but relative to all of the other teeth, they remain exactly the same. Those are 5 crank degrees, so 2.5 cam degrees. Well, yeah, for the different speeds there. But yes, these are all done in crank degrees. All right. So what do we do with that? I can show you, or I was going to show you how we drop this into ArduStim, but I don't think there's a lot of value in it because ArduStim's a little bit messy at the moment in terms of its code and how we do this. But all you really need to know is that there's a lot of work to set it up in the background in ArduStim. All you do though is simply dump this in. That's the only real change of substance that we're actually making within ArduStim, is dumping this number in, or dumping this field in as a big array. And it will then use that to create your pattern. What does that give us in the end? Okay, let's have a look if the stream gods are with me today. I've hooked up a little cheap little USB logic analyzer here to do some demonstrations today. Now, I would stress that in my testing, this particular little analyzer is not very accurate in terms of timing. In fact, it's downright inaccurate in my opinion. But it's good enough for a demo. It's not a replacement for a scope, but unfortunately I don't have a USB scope that I could use. I really wish I had a big nice fancy scope that had an HDMI output or something like that I could capture. But this will do for a good demonstration. So what we see up the top are 2 inputs for the crank and the cam, and they look pretty much exactly like these patterns here. We can see that there's 2 blocks of 4. There's a block of 4 pulses here and a block of 4 pulses here, with the first one being much longer than the others. These are all 10 degrees in duration. This is 60 degrees in duration. And if we jump back into our pattern here, we can see the same thing reflected. We've got our regular group of 4, each representing 10 degrees, and we've got one here that represents 60 degrees. And this is simply a captured data set at the moment. If I record a new one though, we can see what that looks like in real time. We also have the cam pattern coming along here. Now, the cam pattern here is critical because it gives us a little bit more information than we otherwise would have had, in particular around how we get our phase of the engine, which allows us to have this trigger pattern within 720 degrees rather than just the 360. We can see that there's a couple of things going on with this trigger pattern, and when you first start implementing a decoder for a trigger pattern, you need to look through it and go, what's different about a certain or at a certain part of this that lets me differentiate one area from another. And keep in mind that the ECU doesn't really see these as patterns. All it sees are edges. It either sees a rising edge or a dropping edge, a rising or a falling edge. And that's the same on the crank pattern and on the cam pattern. What I can show you though is that if we want to differentiate how this signal relates to this one, there's an area that we can do that makes it quite simple. And that's by looking at the falling edges on the cam signal. If you look at where they take place, and it happens twice over a single cycle, one after the long duration and one after the short duration, you'd say, okay, why don't we just look for a long and a short one? And you can do that. It's not particularly accurate though, particularly during a cranking scenario where the engine RPMs are rising and falling very, very quickly. And the time it takes to go 210 degrees might be changing very, very rapidly during that time. And in the next cycle, when you've got one that's high, that's only 150 degrees, it might be very, very easy to mistake 150 for 210 or vice versa because the engine has rapidly accelerated or decelerated due to the cranking. That's why it's very, very difficult to do accurate syncing based purely on timing alone of a pattern like this. So what we do instead is to say, okay, these falling edges, they take place twice across the 720 degree cycle. However, if we look at the first one, when the cam signal is falling, the crank signal is high. But if we look at the second one here, the cam signal is falling and the crank signal is low. We immediately then have a differentiator that will give us the information we need to be able to get sync within 720 degrees. We know that only occurs if we're looking at the falling edges of the cam signal. There's only one place in the entire 720 degree cycle where this set of circumstances is occurring, where this cam signal is falling and the crank signal is high. So that immediately, regardless of what the speed is, regardless of how quickly the engine is accelerating or decelerating or bouncing around because of the compression during cranking, that's the only point in time where we'll have that set of conditions. And that is what we use to determine sync. Okay, so I'm going to jump into some code now and show you what that all translates to in terms of setting up this actual pattern. Where are we? Okay. So I mentioned earlier that there's really two pieces of information that we need to get from a crank signal. One is the RPM and one is the crank angle itself. For that, we have two functions within the code, and every decoder needs to have these functions with obviously a slightly varied name, but get RPM and get crank angle. Now, every single decoder that's in this file, and it is a big file, will have those two functions just with its name appended on the end. We also have a couple of other functions that are mandatory. There's a setup function, which gets run at the start. There's a trigger pry function, which is called every time we see a primary signal. The primary signal is typically the crank signal. So every time we get the chosen edge on that signal, this function will get run. We have a secondary trig sec, which is again the same but for the cam signal. And there's another one here which is a little bit of an odd one that I'll talk about at the end if we get time, but is not too critical, and that's trigger set end teeth. But I'll talk about that a little bit at the end. So we're going to do a few things in terms of setting this up. There is a line that takes place in the init file as well, and all we're doing here is saying, okay, the trigger handler function is 420A, trigger secondary handler is 420A. The decoder has a secondary input, which is mandatory. We're just going to set that to true. The get RPM, get crank angle, and trigger set end teeth functions are just set to the 420 versions. This is all just part of the basic setup and isn't too critical to really talk about. There's nothing exciting going on here. And here though is where we set what edges we're going to monitor, whether we're looking at the rising edge of the pulse or the falling edge of the pulse. For now, I've made the the crank input configurable in Tuner Studio. Realistically though, it should always be the falling edge, so I'm probably going to go back and change it. This decoder pattern is still in testing at the moment, but that will probably be changed to a mandatory falling, just like the secondary trigger edge is here. So you can see that with the secondary trigger edge, I'm not looking at the configuration, the config page. I'm just setting the trigger edge straight to falling. And then I use those two values to set some interrupts up. And so those interrupts, whichever edge we've chosen, be it rising or falling, will call these two functions, the trigger handler and the trigger secondary handler. Okay, so that's just a bit of glue to hold the whole thing together. It's not actually anything that's making this particular pattern work, and this is largely the same for all of the patterns that we have here. All right, so let's get into the meat of it. What's this decoder actually doing? We've got an array here called tooth angles, And this is what's used. I use this one typically on any of these application specific patterns that I mentioned. On the generic ones, I don't use this because it can be difficult or impossible to know this without recalculating it every time we start up. So there is one decoder that handles missing tooth, right? That missing tooth can have 60 teeth, it can have 36, it can have 24, it can have 12. Now's probably a good time to jump back to that question around how much benefit do you get from adding additional resolution. In my testing, and this is just my experience, and other people will have their own opinions, the sweet spot for sort of teeth versus lower overhead time is somewhere around 24. Beyond that, the accuracy benefits that you get start to taper off pretty sharply. By about 36, I mean 36 is a great wheel. It's a very, very common one, very, very easy to use. I'd recommend it. I do recommend it on a lot of setups. It's a terrific compromise or terrific balance of resolution and low overhead. The difference in accuracy between 36, so 36 minus 1 and 60 minus 2, which are both pretty common patterns, I see almost no accuracy benefit between the two. There is some very, 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 very small amount, but it's pretty much irrelevant. The jump from say 12 to 24 is pretty significant. You get a good increase there. The difference between 4 and 12 is night and day. It's huge. A 4-tooth wheel versus a 12-tooth. A 12 is leagues better. Whereas the difference between a 36 and a 60 is almost unnoticeable in terms of accuracy. Is there a minimum resolution? Well, I mean, 1, I guess. I would say realistically your minimum should be 4. Even that's not great though. Personally, I wouldn't like to run something if I didn't have to that's less than 12. So that was a question from Paul there around minimum resolution. Have an application for a 12 cylinder with 12 teeth for RPM and 1 open slot for cam. Yep. So 12 is okay. I would be quite happy running a 12. If you can drop a 24 or a 36 on, yes, you will see some benefit going to either one of those. But 12 is pretty good. I'm quite comfortable with 12 and the accuracy that it provides. I find that if you do go down to 4 teeth, you have to start doing tricky things with the pattern that are specific to that pattern to try and get a little bit more accuracy in. If you were to simply have a 4-1 wheel, so a wheel that literally only had 3 teeth on it, and you ran the missing tooth decoder, accuracy would suffer. There's no question about that. The 4G63 pattern though, which is really common, and it's what's used in Miatas, which are probably the most common users of Speeduino at the moment. There's a whole bunch of little tricks that I've used that are specific to that pattern that looks at the relative angles between crank and cam and all this sort of thing to try and get some better resolution, and it comes out okay. It's not great, but it is okay. So you can do some tricky stuff like that, but if you're just looking at a generic wheel, then I wouldn't run 4 teeth. Would a 60 minus 2 benefit sync speed? Yeah, it can benefit sync speed. You get sync within half a revolution as opposed to a full revolution, so there is some benefit with that. The same would go though for a 36 minus 2 wheel though, Keith, which is what you get in Subarus and things like that. So all right, to jump back to this pattern that we're looking at, if we where is it? If we have a look at the pattern here, if you count the number of, let's say, falling edges across the crank cycle here, you'll get 16. That's across 720 degrees. Group of 4 here, group of 4 here, that's 360 degrees, and we just have that repeating again over 720. So in total, we've got 16 teeth that we watch here, and so we've got an array here of 16. If you're not familiar with arrays starting from 0, I would urge you to get comfortable with that. But in C, yeah, array start at 0 rather than 1. So we have angles from 0 up to 15. And again, we're going to start seeing some pretty familiar numbers here. 711, which is the magic angle that this represents here. So we're going to call this edge here tooth number 1 because it's a nice, easy to identify place within the pulse train, and it happens just before, or is the one that's most relevant to cylinder number 1, top dead center. So that's what we're going to call tooth number 1. And yeah, it takes place at 711 degrees. All of these ones, you can calculate them for yourself, but you'll get the numbers that I've gotten here. Now, they come in, like I said, groups of 4. So we've got 111, 131, 151, 171. Now, a comment here saying just before number 3, top dead center. And that's what this group here represents. We know that they're all 20 degrees apart because the diagram helpfully shows us that we've got 9 degrees, 29 degrees, 49 degrees, and 69 degrees. So this little block here of 4 is represented by these 4 entries here. And all we're going to do is go through and repeat that, adding 180 and 360 and then 540 to each of those. And you will end up back at 711 for this one here. Okay, so that's really the most critical thing that we need to get right. And then we're going to use that data down here to determine our crank angles once we've been able to get both sync and RPM. And I'll keep coming back to those two because they are both really critical pieces of information. We've got a couple of setup things here. Not all of these are actually finished for this pattern. We've got a filter time. Now, I've yet to write the filter code for this. This is using just a generic filter, but it unfortunately will require a specialist filter because not all of these gaps are equal. We need to take that into account when we're filtering. All right, most of that is just setup code. So it's saying what our current tooth count is. We're just going to set it to 1, just as a default. Sync will be set to false anyway at the start. So until we've declared sync, until we've declared that we have sync, it won't run anyway, and this won't mean anything. But these are just giving some sort of sane default values to make sure that they're not, 300, for example, for the tooth current count. Okay, so we need to start looking at 2 things. And what I mentioned before was how we're going to determine sync on this engine. And we're going to determine it at this point here. Okay, so we're going to be watching these 2 cam signal edges, this one, and looking for this place here. And it's pretty simple to do. And that's why I like this pattern actually, because it turned out to be relatively straightforward to code, even if it looks a little bit weird at first glance. So I'll come back to the trigger pry, or the primary function in a minute, but we'll have a look at the secondary one first because that's where we're going to get sync from. So we know that this function will get called whenever the secondary signal is falling. So it will get called twice every 720 degrees. So all we need to do is figure out whether we're in the first one or the second one, which is relatively straightforward. All we do is in here we've got a function or a nice little macro that exists for all of these called read pry trigger. And all of that does, or all that does I should say, is check whether the primary trigger is currently high or currently low. If it's true, it means that signal is high. If it's high, we know exactly where we are. And for that matter, when it's low, we know exactly where we are as well. So that's our reference point. And all we do is say, okay, if sync is currently false, that's great. We don't have sync yet. We're going to say, okay, we now have sync. We're going to declare has sync to be true. And we're going to set ourselves to tooth current count 13 now. We can figure this one out. We know that this is tooth number 1 here. So if we work our way backwards, we've got tooth number 16, 15, 14, but we haven't reached this tooth yet, right? We're only at this point here. So the last tooth that we've seen on the crank is actually this one, all the way back here, which is tooth 13. That sets us up to say that we know where we are now on the crank cycle. The current count is 13. The next crank tooth that we're going to get is this one, which is 14. So we know exactly where we are, and that's good. We do another little check here as well, though, to say if we do have sync already, right? So this is our case when we don't yet have sync, so when the engine is first starting. If we do already have sync, though, so the engine is already running perhaps, we're going to check and make sure that we're actually at tooth current count 13. Now what this is doing is saying, okay, we've got to this point in the engine cycle. Have we counted or have we seen the correct number of crank teeth to get us to that point? And this is a check. This is how we determine that we're still getting a good crank signal and that we're not getting a whole bunch of noise or issues with that signal, or missed signals, for example. If it's not equal to 13, then we've got a problem. We increment the sync loss counter and we set the tooth back to 13. So we keep sync. We don't say, hey, we don't have sync anymore, because we still know where we are, but we do have to indicate or flag that we've had an issue. So we increase the value of the sync loss counter here. Okay. So that was what was happening when, or that was what we did when the primary trigger was high. We can do basically the same thing when it's low as well. So secondary signal is falling and primary signal is low. Secondary signal is falling, primary signal is low. So we know we're at this point, and we can count the teeth here. So we've got tooth number 1, 2, 3, 4, 5 was the last one. And that's exactly what we do. We set the tooth current count to be 5. We declare sync. We do the same inverse check here to make sure that we haven't lost sync. And we're done. That is what, for this particular pattern at least, gives us sync. It really is that simple. Some other patterns are much more complex than this. This one turned out to be a really nice simple one to write. Okay, so that's what we do every time we see a secondary trigger. What happens when we see a primary trigger? Now again, this one is relatively straightforward. We capture the time that we saw it, current time. We capture the gap, which is simply the current time minus the last tooth time. So it's how long it took to get from this point to this point, or this point to this point. And we compare that against a filter time. Now, as I said, I've still got to implement the filter system properly for this one, but you'll get an idea here of what this filter is doing. It's saying, has it been at least a certain amount of time between these pulses? And we calculate this trigger filter time based on the current RPM and how many degrees we expect before the next tooth. So for all of these ones here, we can use the RPM, so the speed, and the fact that we know that there's 20 degrees between each of these teeth to figure out how long it should take to get from here to here. And we set a filter to say, okay, anything that's less than, say, 50% of that time cannot possibly be a real pulse. It has to be false. It has to be just noise in the system. So depending on how aggressive you get with your filter, that might be 25%, 50%, or 75%. You have to have some allowance in there for changing of speed, so the RPM will move, hence why you can't just say 95% and filter out everything less. Generally 50% seems to be a good number, but it depends how aggressive you want to get on your filtering. That's all we're doing here, is saying, is that gap time greater than our filter time? If it is, we increase the current tooth count, so we know that we've gone to our next tooth. This is a valid pulse. We flag it as being a valid pulse, so we say valid trigger equals true. So flag this pulse as being a valid trigger, i.e. that passed the filters. This is simply some handling for startup to say if tooth last tooth time, which is the time it took to go from the last tooth to the current tooth, is 0 or tooth last minus 1. So we actually record not just the last amount of time to go from here to say if we're on tooth number 1, we record the amount of time it took to go from here to here, but we also keep the amount of time it took to go from here to here. So we have a little bit of history there that we can refer back to. Okay, we then check our tooth count. We know that we only have 16 teeth in this particular pattern. So we say, if our tooth count is now, after we've incremented it up here, if it's now more than 16, we know that we've started a new cycle, right? We're at the end of one revolution and ready to start another one. And we just check there that we've got sync. So we set the current tooth count back to 1. We have this time that we also, oops, didn't mean to do that. We track the time that tooth number 1, we track the time that the tooth number 1 was last seen. So we say tooth 1 time equals current time, which we set up here. And this is all in microseconds, by the way. And we also record the time that the last revolution took place. So tooth 1 minus 1. So we know when the current revolution started, and we know when the last revolution started as well. So we know how long it took to do a full revolution. And that's what we use to calculate our RPM. I'll show you that in a minute. And we also increment another counter called start revolutions, which is simply a counter of how many revolutions the engine has made since we got sync. Okay, we do a little bit of filtering stuff here. This is not yet complete for this decoder, but it's sort of what I spoke about before in terms of how we set that filtering time. And we have this. Now this is, I shouldn't call this experimental anymore. This is the new ignition mode that some of you might have seen. I'll talk about this in a minute because it is important, but I want to show the output of all of this working before then. So the other two functions that I mentioned, which is the ones that the ECU is actually needing, are get RPM and get crank angle. RPM is really, really straightforward. All we do is say, well, we've got a nice little macro here called standard get RPM. So this is a common way of getting RPM that is common across just about all of these decoders. Not all of them, but most of them. All we do is pass it, in this case 720, because we need to know whether the revolutions are happening or whether we have data over 720 degrees or 360 degrees. This standard get RPM function, it does a bunch of checks just to say, okay, do we have sync? Do we have, or are we cranking? Is current RPM less than the cranking RPM? But the meat of the code here is that we're going to get the revolution time, so the time it takes to perform a single revolution, which is the time that we last saw tooth number 1 and the time that tooth 1 was seen previously. That gives us our revolution time, so the time it takes to perform one revolution of the engine. Sorry, it's not quite correct. One revolution of the entire cycle, and we need to know whether that's over 720 or 360 degrees. And then we just do a little bit of maths to get our RPM. We use the number of microseconds in a minute, dividing it by the revolution time, and that gives us our RPM. Fairly straightforward, but it's a nice simple way of getting RPM. Okay. So that's our get RPM function, relatively straightforward. Our get crank angle function is slightly more complex, but not too difficult. You'll notice that I have these sections in here called no interrupts and interrupts. Those are critical because these two functions up here, the trigger sec and trigger pry functions, they can run at any time. That they will happen as interrupts to our normal code. So what we don't want is to begin calculating our crank angle, right, with the current tooth count, and then have that current count variable change whilst we're halfway through our calculations. If that happens, we get false data. We get something that's meaningless, and we'll get an RPM spike or we'll get an RPM dip, and we're going to run into problems. So what we do is declare this section here to be a no interrupt section. So no interrupts can happen between these two lines. And all we're going to do is store the variables that we need that might potentially change during those interrupts. And we're just going to store them in some temporary variables. We know that those temporary variables aren't going to change, right? These ones here, the tooth current count, last tooth time. I don't know why I made these variables so hard to say. They might change, but the temp versions of them that we've stored won't change, which is what we want. So what we're doing is we're going to store what the current tooth is, so where we're at, what our last tooth seen was. We're going to store what time we saw that last tooth, so what time in microseconds that tooth was seen. And we're going to store the current time in micros that we're doing this calculation. This is just used in other parts of the code to know how fresh, for lack of a better word, our crank angle calculation is. Okay, so we say our basic crank angle here is whatever our current tooth count is minus 1. So if we're at tooth number 1, we're going to look up position 0 in this array. So this is getting back to the array that we had here, the tooth angle array. If we're on tooth 1, which is this one here, we need to look up array slot 0, which is what this is. So we say tooth current count minus 1 plus any trigger angle. Now this is if someone happens to have added a few degrees here and there in the actual trigger settings in Tuner Studio. For this particular pattern, I would only expect this number to be very, very small, sort of plus or minus 5 degrees, just in case the crank pattern has moved around a little bit. But generally that should always be 0 for this pattern. So that gives us the angle of the last tooth that was seen from the crank. We then need to calculate how far in terms of angles we've gone past that tooth before we've got to the next one. So estimate the number of degrees traveled since the last tooth. We calculate the time since the last tooth. So what time it is now, micros, minus the last tooth time. So that's how many microseconds have passed since that tooth. And then we've got a little function here, or a little macro here called time to angle. And this does exactly what it says on the lid. It takes a certain amount of time, in this case our lapse time, and converts it into the number of crank degrees that time would have taken. Now there's a couple of different methods that you can use for that. Some are more accurate, some are more susceptible to noise, all this sort of thing. But so this is just simply one method that's called the interval revolution. So it's using the total revolution time, which averages things out a bit nicely, to calculate the current speed, the current angle based on that speed, or based on that amount of time. You can use the interval between two teeth as well, but that means you're more susceptible to noise, and you're more susceptible to very slight variations in the crank wheel. So if you've ever seen a tooth trace, for example, where it might be a 36-1 trace, and not every tooth is perfectly flat along that trace. You obviously get the one jumping up for the missing tooth, but not all the others are exactly the same. They're a little bit bumpy. There's a little bit of variation in the actual accuracy of the wheel itself. And that's why you don't always necessarily want to use the interval between two teeth to calculate your exact angle. You want to average it out a bit more, so we use the interval of the entire revolution. Keith asks, is there a resolution benefit from running a higher tooth count of 36 for missing tooth cam only detection? If I'm understanding you right there, Keith, do you mean If you're running a missing tooth wheel on a cam, so as opposed to running it on the crank, is there a resolution benefit for going higher than 36? Well, yeah, it still exists. Because you're running it at cam speed, you're effectively halving the resolution of your wheel. So your 36 minus 1 on a cam is equivalent to sort of an 18 minus 2 on a crank. So yeah, there can be some benefit to going higher than 36 if you're running it at cam speed. Okay, so at this point we're going to add that little bit of extra time on to our crank angle, and that is the crank angle that we're currently at as of when this function gets run. We do a couple of safety checks. We make sure that crank angle is not above 720. We make sure it's not above the crank angle max. Now the crank angle max is set by the ignition and injection timing settings. If both of those are set, for example, to wasted spark and paired injection, it means that we're only running the whole system over 360 degrees. There's nothing in that timing that requires more than 360 degrees. So in that case, the crank angle max gets set to 360, and we make sure that our crank angle output sits between 0 and 360 only. We never will go past 360. And we make sure it's not less than 0. So these are just a couple of safety checks. And then we return the crank angle, and it's that simple. So we've now got the two pieces of information that we needed that were critical, the RPM and the crank angle, determined from a pattern that looks like this. So at this point we have a working decoder, and that's exactly what we see in this pattern here. We've got a crank in our cam that we saw before, and we've got two ignition pulses. Now in this case we see that the ignition pulses are wasted spark, and we can tell that because we know that a full revolution is going to go across here, and we've got two ignition pulses happening in that time, so we know that it must be wasted spark. And sure enough, if we jump into Tuner Studio here, we can see that we're running wasted spark. Just to prove that I'm not a complete and utter liar, I'm going to set that to sequential. Or restart the unit. Go back into our logic software. We'll do another trace. And you can see now that over the same 4 cycles, we're only getting one ignition pulse. You also see that this ignition pulse has moved over. So now it's because we're expecting that there will be a third and a fourth ignition pulse. I don't have traces set up for those, but we know that they would exist because we can see that these are now spread out in a pattern that would be 3 and 4 completing your cycle. So this is our cycle here. We're starting from tooth number 1, running all the way up to tooth 16. Tooth 16 over here. So yeah, that's our working trigger pattern at this point. The one other thing I was going to mention, I'm just looking at how we're going for time. Oh, right on the hour. Okay, this one should only take a minute. This set end teeth function here. This is part of what I tend to refer to as the new ignition mode, simply out of habit now. But it is, by default, it's turned on for most of the most of the triggers. My apologies, I've got a bit of a cold at the moment, so my voice is a little bit rough. What this is doing is saying, okay, instead of just calculating the ignition schedule time, so when the ignition should fire arbitrarily at any point, what we're going to do is say whatever the last tooth before the ignition pulse time occurs, whenever that trigger happens, we're going to do a recalculation of that ignition schedule just to make sure we're absolutely dead accurate. These points, when we see these teeth in the code, are the only points in time where we can be absolutely 100% certain of what the crank angle is. We can estimate it at any other point in the cycle, but it is simply an estimate. These points, though, we can be absolutely certain of what the crank angle is at that point. So if for example, we wanted the ignition pulse on cylinder number 1 to be occurring at 5 degrees advanced, we would know that, which is about here in the cycle, we would know that the tooth that comes immediately before that is tooth number 1, because we know that tooth number 1 is at 9 degrees before top dead center. What that means is that whenever we hit tooth number 9, we want to do a recalculation of when that end time should be, so it is absolutely accurate. This is what I skipped over here. So new ignition mode. We're saying if we've got this mode turned on, we calculate our crank angle, and then we run a macro here that compares our current crank angle, which again, because we're running within the trigger function, we can be absolutely certain is correct, and our tooth current count. And what we're going to do is say if that tooth current count equals the one immediately before when the ignition pulse is going to happen, or when we want the ignition pulse to happen, do a recalculation of this. Now, it gets a little bit complex how exactly we determine that. For this pattern, though, it's nice and simple. We simply say, if the ignition advance is less than 9 degrees, so anywhere between here and here, then we simply use tooth number 1 as being that reference point. If it's, or else if, so if we're less than 29, oops, put that back in, it means that we're between here and here. So we set it to be tooth 16, which is this one. If we're more than 29 degrees of ignition advance, we're presumably or assumed to be between 49 and 29, then we set it to 15. This trigger pattern makes a lot more sense when you realize that this is what the OEM is doing as well. And that's why before each of the cylinder top dead centers, you have this little series of pulses to give you absolute timing markers. So that's as good a sign as you could possibly want, that this type of method of guaranteeing certain timing is exactly what the OEMs would be using. They don't care about what the timing is here, or here, or here, right? Because no ignition events are happening there. They don't really care about what the accuracy is of the crank trigger at any point other than immediately before each of the top dead centers, so immediately before when the spark is going to occur. And that, all of a sudden you realize why this trigger pattern makes sense. Instead of having a continuous stream of teeth in here, the designers have gone, hey, we don't need that. All we need to do is just have a few of them before our top dead center points, and we can get all of the benefit out of them without having quite as many interrupts. And when I realized that, all of a sudden this pattern makes sense. I haven't seen another pattern that was exactly like that. Most of them just have all of the other teeth in here as well. But when you think about it, you don't actually need all of those. You really only need them around the points of top dead center. Now again, this only works because this is one of these fixed patterns, not a generic pattern. You can't just plop this on an engine and move these angles around and put tooth number 1 wherever you like, because they have to be relative to top dead center. All right, so that's just gone a little over an hour there, and I've covered most of what I wanted to sort of discuss. Does anyone have any questions or anything that they want to ask about that? Let me try and catch up with chat here. Oh, you're all a fairly quiet bunch today. Not too many questions. Well, look, guys, I hope that's been useful to you. I'll finish things up there. As always, if you've got any more questions, feel free to ask on Facebook or in Slack. But yeah, hopefully it's been an interesting session for you. Oh, I've finally got some questions coming through. Are there any advantages to the Subaru trigger pattern? The Subaru trigger pattern has the advantage over a regular 36-1 pattern that you could get sync twice in the engine cycle rather than just at one point. So instead of having to wait for one full engine revolution to complete before you can get sync in 2 different places. That's really the only advantage. Otherwise it works much the same way as any missing tooth sensor. Do we tweak generic position with trigger angle? I'm not sure I entirely understand the question there. Do you mean in that case, if the wheel has moved ever so slightly, how we take that into account? I think I get the question, and that's saying if somebody's used a trigger angle here, so let's say they've set that to 10, how do we take that into account here? If that's the question, currently I'm not handling that. I should, and I probably will. That's where it gets really, really complex on the generic triggers. So if I have a look at the missing tooth, decoder, it's a lot more complex because it has to deal with generic situations. But if I have a look at, here we go, that set end teeth function, here we have to take into account the trigger angle and how it relates to everything else, and it gets a lot more complicated. And this is why I talk about that fixed pattern being simpler to write a decoder for than the generic ones. These generic ones, you have to account for a lot of different weird edge cases and things that you can be certain won't happen on a fixed pattern. I don't know if that answers your question. I'm not even sure if that was your question, but it might be interesting. Okay, guys, I'm going to wrap it up there for this week. This was a bit of an in-depth and slightly more technical session than some of the other ones that we've had. But I hope it was of some value to you. If you've got any suggestions for things that you want to see in future streams, of course, just let me know. This one here came out of a suggestion that someone made about a week and a half ago. So I'm always looking for things to talk about that people are interested in. So, okay, guys, hope you have a great rest of your weekend.